இப்போ பாருங்க சார், வந்துச்சா? இப்படி திருப்பினா லேண்ட்ஸ்கேப் தெரியும். சரியா? ஓகேவாங்க சார்? வெர்டிகலா வச்சிருக்க அப்படி திருப்புங்க. சரி, வெர்டிகலா வச்சிருக்கேன். ஆமா ஆமா ஆமா. லைவ் போகுதுல்ல சார்? ஓகே சார், கட் பண்றேன். ரீல்ஸ் எடுத்துட்டு மைக் இருக்கா? மைக் ஆன்ல இருக்கா? ஆடியன்ஸ் எடுத்து இது எடுத்துருங்க. கீழே
Keep silence. Please be calm. Ready, sir? Please be seated. A very warm and pleasant morning to one and all gathered here. ஒருமைக்கண் தான் கற்ற கல்வி ஒருவர்க்கு எழுமையும் ஏமாப்பு உடைத்து. Every day is a new day, a new chance, another opportunity, a new beginning. Embrace it. Make it a great one today by attending our 2-day international conference on computing and intelligence system organized by the stream of computer science, Sri Krishna Aditya College of Arts and Science. Work as if everything depends on you. Pray as if everything depends on God. With the amazing quote, I request everyone to raise up for the Tamil Thai Valthai. Thank you. Thank you. Light is a symbol of brightness and prosperity. We should be shining lamps, giving light to all around us. Now, let us invite our dignitaries to lighten the Kuthuvilasu. Now I request our beloved Principal Ma'am to present a bouquet to our chief guest. Thank you, ma'am. The greatest leader is not necessarily the one who does the greatest things. She is the one who gets the people to do the greatest things. With this inspirational quote, I welcome our beloved principal ma'am to deliver the felicitation address.
Good morning, students. It's my privilege and honor in joining with you all to welcome our guest, the resource person from Kazakhstan, Dr. Ardar from the University of Kazakhstan. And it is a pleasure for us to have him amongst us today to deliver the keynote address on neural networks. Actually, he's a mathematician and who is specialized in mathematics and biological sciences, right, sir? And not only that, it's today he's coming here and then giving keynote address and then giving, but I expect him to have more contact with us and maybe not in person, even through online, he can contact us and he can deliver and share his expertise with our students and with our research scholars, particularly the computer science stream of faculty members. And even we can think of having joint ventures, the projects, the research collaborations with him and with his department. And maybe that is what we are actually looking for, and hope that we can have a further discussion with him regarding that. And I take this opportunity to congratulate all the faculty members of all the computer science streams, BSc Computer Science, BSc Computer Technology, BSc Information Technology, BCA, BSc Data Science, and BSc Artificial Intelligence and Machine Learning. All the departments have joined together and organizing such international. This is actually the second edition of the international conference, and I hope that this will continue year and year, in even still better. Always we will not sustain with whatever we have achieved. We still always we look for what more we can achieve. So that is how we are growing, and you all know what is the stage that we have reached within this short span of 7 years. And all the topics that has been chosen by the departments are really very useful, and it is the need of the hour. I think they have chosen the artificial intelligence, neural networks, computational fluids, and IoT, and so on. And everything is being really useful, and many research scholars are pursuing their research in that area. And I look forward that all our students, so particularly all the third year students, should come forward to present papers in the conference and also to publish papers, and even second years also. And this is the right time for you people to start working on papers and then try to publish it either in the conferences, conference proceedings, or in well-reputed journals. With the guidance from the faculty members of computer science. It's a great pleasure for me to be amidst with you people, and then going to listen to Dr. Adak, who is going to share us knowledge on neural networks. With these few words, once again, I welcome Dr. Adak, the professor from Kazakhstan, to our conference, and I wish. Actually, almost this is the second day, and it's really a successful one, the conference. And once again, I congratulate all the faculty members who have taken a lot of efforts in making this conference come to reality and in a grand manner. Thank you.
It is the supreme art of a teacher to awaken joy in creative expression and knowledge. With this motivational quote, I welcome Professor Lakshmi Devi Department of Computer Science, to introduce the guest of honor.
Good morning to my network. It is my great privilege to introduce today's keynote speaker, an eminent personality, Dr. Arthur Hasno Graves, Department of Mathematics, Nancy Bayes University. Has completed PhD in Mathematics in Middle East Technical University, Turkey. His research interest includes emotional biology, mathematical analogy, nonlinear differential equations, mathematical neuroscience. He has received research grants from Ministry of Science and Education, Kazakhstan. He has published in any number of journals, art, book chapters, monograph in Scopus, IEEE, and in science journals. He has invited as a chief guest, keynote speaker at many international conferences. He is guiding many PhD scholars. The most attractive man is a hardworking man. He has such a hardworking, long perspective, visionary guest with us. Welcome you, sir.
Thank you, ma'am.
Okay. It's my pleasure to be here. So this is the first time I'm visiting India. So my first speech will be in this college. I was surprised and honored to know that the principal is also a mathematician. So it's truly inspiring. How many years he devoted in science and administration. Okay, so I'm coming from Kazakhstan, which is in Central Asia. Okay, so it's like bordering on the north with Russia, on the east with China, on the south with other Central Asian countries like Kyrgyzstan, Uzbekistan, and Turkmenistan, on the east with Russia and Caspian Sea. So we are landlocked country of size almost like India, but the population of 90 million. Only. So this is a little bit of history of the country itself. The place I'm coming is as you can see, it's in north, and we have winter right now. I already told that it's minus 20 right now. Okay, so the feeling temperature is minus 25 or something. Okay, so the weather is not very warm here, and in addition to that, I got very warm welcome from Tamil Nadu people. I like this place very well. Thank you. So with this note, I'd like to start my talk, which would be on well, this is the model itself is neural network model, but I'll be talking about synchronization, in particular applying sliding mode control, and you'll be surprised maximum principle. Okay, so I guess many of the students here to calculus and real analysis, I guess, right? You took calculus, right? So you'll be surprised that even with that kind of knowledge, you would be differential equations and combination with calculus, you can derive some good results. So that would be at the end, but now I'll start with synchronization, right? Okay, so next slide. So what is synchronization? So synchronization is one of the universal concepts. Okay, so you can observe it in the nature event, starting from fishes, right? If you like fish, they swim synchronized sometimes, right? Even birds, so starting from fish to birds, some type of birds they also fly synchronized. So this is a universal concept that we study in mathematics too. So what is the synchronization? So it is when in terms of mathematics we look at dynamical systems. So we model them using mathematics, and we look at when this two or more dynamic system can converge to some designed target within some time. Okay, so the some time is important. Okay, so like in the past, like starting with asymptotic synchronizations, when you look at as time tends to plus or minus infinite. Nowadays, we study from application point of view, finite or fixed time, because your engineers are interested in, you said me, give me time. I'm not interested at infinity. I'm really interested. What happens finite time? Tell me, like 5 seconds, 10 seconds, for days, for hours, right? So, so this talk I'm talking about synchronization concept in finite and fixed time. So what we do is we design here a controller to a model, neural network model, which I will present later on, to shorten the setting time. So the settling time is important. So how many seconds? What is the settling time is important, okay? Because you might not have in application the desired time to reach that synchronization. So we understand that that should be finite and should be short. So this next slide. So yeah, here are the possible applications of that, which I don't study as a mathematician. I just mentioned those applications, okay? So there are, as you can see, many applications of synchronization starting from image processing to power converters. Okay, so biological systems, that's something we obviously study. And in this study, in this presentation talk, I don't give any applications, but hopefully next time I'll be able to, if you invite.
Sure.
So I'm currently on the stage of applying what we obtained to image processing. But the other applications also could be considered. Okay, so here I just mentioned them, but I don't have time and results to present right. So here is the model. This one is the we say that drive system. Okay, so here the main system is it's called shunt inhibitor neural network. I will present what this each term is on the next slide. The main difference from other neural network models is that sum. Okay, so the sum is usually if you look at CNN models, you will see that other models, you will see that they sum all nodes. Okay, they sum all of them. But from application point of view, sometimes, especially in image processing, you might be interested in only neighboring neurons only. Okay, so for example, if you want to, I don't know, recover some part of the image, but not the whole image, right? So you don't need the whole neurons. Okay, so you just need the neighboring ones. So that's to emphasize the sum is CIJs, which are postsynaptic coefficients, which I will present on the next slide. It is summed on the R neighborhood. So this R neighborhood you choose yourself. So here, IJs and HIs and LJs here are bounded by R. And these are, depending on your problem, you can choose yourself. So, if you want to sum them all, it's also possible to generalize it. You can sum it all. But if you want to keep it local, you do it local. So this was, like, the model itself was first proposed by Pinter, more than 20 years ago. And in our study, we adopt this. Okay, so this one is called drive system. Drive system. The neural network models itself, I'll show you simulations, do not synchronize. Okay, so you impose some conditions, you can make it stable, but to make it synchronize, we actually imply some control to it. Okay, so this one is we consider as the driving model, to which we consider later on I will consider a response system, a response model, which is with the control. Sometimes they're called master and slave system. One is a master, one is a slave system. So here we call it drive response system. This next slide. So here are the notations that I promised to show you. These XIJs are voltages on the cell CIJ. EIJs are external input to the CIJs. And here we assume that these external inputs are bounded from both above and below. So they are bounded functions. So alpha IJs, the coefficients of these XIJs are passive decay rate, and we assume that they are positive definite. And CIJs are connection or coupling strengths of this post-synaptic activities, and they are assumed to be non-negative. So we consider this model with a delay. Well, there are various reasons why we consider the delay model. Might be due to the hardware, like you have some, or yourself. So then this delay could be, you could consider in the application, if you look at the literature, that are different delay models, and here we consider a continuous time. So we say that delay is not a fixed one. It could be different for each node, but for each voltage node. And we consider here to be a continuous function, which is non-negative and bounded. Okay. And an activation function, F is an activation function, representing the output or a firing rate, and we have some notations. So let's go to the next slide. So here, this CIJ, this coupling strings, we consider them to be discontinuous function. Okay, so there is a threshold value, theta ij, upon which if you reach that threshold value, then it fires. Right? So then this coupling strings are discontinuous. They are like step functions, heaviside functions from mathematics. So these are like if you reach the theta ij, then it is hat, right? So there are like different notations. So they are discontinuous. So this is we use in mathematics to capture the event of memristors. Okay, so if you are considering memristor neural networks, then these coupling strings are considered to be discontinuous, or at least. So here, as I said, to the drive system, we consider a response system. The main difference here is the function Wij that we have here too. Okay, so Wij is a control function that would be designed in. Since I was told that I will be giving mainly main elements for the students, I will explain in few slides, in next slides, what this sliding mode control is. But here at the moment, I say this is a control mechanism which will be designed. Okay, so that if you apply this to drive system, response system, these two systems, like 1 and 2, will be synchronized, and I will show simulations. So what we do here is we consider the error function, which is the difference between drive and response system. Okay, so ideally we want, we have a differential equation for the response system, which is the Please, to the next slide. So here, obviously, we made some assumptions on this functions. Okay? So there are two main assumptions we make. A1 is that the coupling function, activation function F is a Lipschitz one. Okay? So it satisfies Lipschitz, and that we assume from a mathematical point of view for a reason. Okay, so that is to ensure that your model has a unique solution. Okay, so uniqueness is provided by this Lipschitz continuity. Okay, so then the next, the second condition is that we assume that this activation function is bounded. Well, this is again, we want to study bounded solutions. Okay, so you don't want to study a solution which becomes unbounded. So in fact, so which blow up, basically we say blow out solution. So they are unbounded in finite time. Here we assume that these are bound activation functions which will imply that your solutions are bounded. Well, so here we give the definition, which could be found in many papers. Here I cite Cohn's paper, so what do we want? Okay, so we want this error function, which is the difference between drive and response system. So we want them to converge to zero at a finite time. Okay, so this time is given by t squared. So you want this limit of this function tend to zero as t tend to t star. And after that t star, you want this error function be identical equal to zero. So finite time error tends to zero, then it's identical. So if it is satisfied, then you say your system achieves synchronization at finite time, and this time t star. An important note that it might depend on your okay. So so you took calculus course, right? So like continuity, right? So if you apply epsilon delta definition of continuity, right? So that epsilon will depend on delta and x0, your initial condition. So here it is the same. Like we are talking about the limit, but this limiting time somehow might depend on t0 and your initial state. Okay, might depend. So that's no problem. As soon as you have these two conditions satisfied, then we say that it is finite time synchronization. But in addition to that, if your settling time doesn't depend on x0, the initial state. So then we say it's fixed time. Okay? So it's like in mathematics, if you remember, like we have different continuities, right? We say continuous, uniform, continuous. Uniform continuities if it doesn't depend on the initial state. So here it's somewhat similar. Okay? So finite time, if it depends on initial state, fixed time, so it doesn't depend. So which is considered to be is like advantageous sometimes. Okay, so you don't want to be like bounded to initial conditions. So you want it synchronized. So you want this synchronized. This one Tmax here we say Tmax. Okay, Tmax doesn't depend on what initial condition you choose. Okay, so doesn't matter what initial condition you choose. Of course, this is more stronger, but you have to assume in general. Other like we got the results to the shunting inhibitor using sliding mode control here on this talk. But previously we got feedback control. Then we had to design different controllers, like to fixed time different controller and finite time different controller. Novelty of this talk here, I will show you that we were able to synchronize using a single control mechanism, one controller, to those. I'll show you later on. Okay. So next slide, please. So here I use some auxiliary lemmas from theory of differential equations, which I think I'm going to skip the proof. That's why these lemmas, I have the proof as well. Okay, so these lemmas, if you are interested, I can share you later on. Okay. So basically, this p function is a Lyapunov function, whatever it means, and we want the derivative to be not only negative definite, but also some post-definite pt minus pt times b to the mu. Okay, so then if these are satisfied, then we use this lemma to prove that we really achieve 550 simplifications. So I'm going to skip this and next lemma. Next slide. And I'm going to skip this one as well. So the methodology we use here, CMS, and C is for sliding mode controller, is we design a surface, a sliding mode surface, a switching surface sometimes, right? And then we design a sliding mode controller. So that after designing the sliding mode controller, we apply Lyapunov stability here. Okay, so to make it clear, so if I apply this on a model I have, which if you haven't seen it before, might seem like scary, right? I designed my model so that I have a simple example for you to solution. Yes, which is not related to neural networks. So please, let me go to the next slide. I have this more. Here, J is the inertial moment. So you consider it to be a constant. Second double prime is an angled signal. Okay, so which is like multiplied by the second derivative. UT is the control input. Here I will show you an example where we sliding mode control, right? And this is a disturbance, which you assume to be bounded. So some disturbance, and then you want to control it. And so you design a control so that this sliding mode S function is equal to C times E plus E derivative. Okay, why I consider the derivative here is because the system is with inertial term. So there's derivative. So here C is a constant which satisfies Hurwitz condition. That's to say, if you have a matrix, that would be you look at every entry. But here, since I have a constant, this basically means that it is positive. But if you are working with the matrices like n-dimensional and you check what this Hurwitz condition is. So let's go to the next slide. So I might be speaking fast, so just let me know if you want me to slow down. Okay? So what you do here is you look at so what the aim is the same like before. Okay, so look at the error system. You want your error system to tend to 0. Okay, so you want your system to be equal to 0 after some time. So here, so ideally what happens? So if this sliding mode S of t is equal to 0, then from the previous slide, if you go to the previous slide, previous slide. Not the previous one. Okay. So this from 5, you see that as function we define C times E plus E prime, right? And go to the next slide. So that would mean no. Okay, here. So here. That would mean that so if you say that this is equal to 0, then C dot E plus E prime is equal to 0, right? So which is a linear differential equation. Here, from here, you can solve this, right? So I assume you take differential equation. Do you? Like I don't know, like computer science, right? So in our university, computer science majors are not obliged to take differential equations. It's like an elective. I don't know. Here, do you have differential equation? You don't have, right? Well, those are linear. We call it linear differential equation, which could be separately solved. The linear ones are easy to solve. So we always say easy, but unless you take the course, I mean, but like, well, so the assumption is that if you have a linear differential equation on C, so you start assuming that it has an exponential solution, right? So that's the assumption. So then you prove that that's really the case, okay? That's, you really have the exponential function. And then you want to make sure that there are no other solution exists. So you prove that it exists. So, like as a mathematician, coming from math department, I have to advertise some math courses. Okay. So the rest is you learn from differential equation course. So I encourage all of you, if you haven't taken, you can see that like this neural network model is quite applicable in computer science. Unless you take differential equation course, this makes little sense to you. Okay, so I highly recommend that you take some upper level math courses. Don't limit yourself with calculus 1, 2. Linear algebra, but you have that should be must. No. Yes, right. Obviously. Because like, well, I'll say this. Okay? So I claim that at least my students tell me that I am the best linear algebra instructor of all universities. So we have the priority with registration. Okay? Like math majors and computer science majors. And my section is full with math and computer science majors. So the computer science major students are equally good as math majors in my section. So like don't limit yourself with linear algebra only. So in linear algebra we also teach you how to solve linear equations, right? Linear matrix equations, homogeneous and non-homogeneous. And in introduction to differential equation course, I will teach how to solve differential equations. So that's a bit advertised to take some math courses, perhaps. So then, in this case, you see that the solution is, as I said, this one is an exponential function, like the initial term times the exponential function, where C is a positive, right? If you remember, C was from Hurwitz criteria. You remember this is a positive constant. Now, what happens? No, this is a calculus question. What happens to this function if you take the limit as t tends to plus infinity? What happens? Let me ask. Let me see if you really take calculus. So x, yeah. So this I consider exponential easy, which is constant. Yes. Yeah. 0. That's right. So like. So this will be an exponential derivation. Well, so what this means? Okay, this means that the speed tracking error will tend to exponentially to 0. That's something desired. Now please go to next slide. So what we do is, okay, so then we look at this s of t is, if you remember, a function of error function. Okay? So this is an error function which you can differentiate. Now what we do is we look at, we want this to be exponentially decaying function, if you remember. Right? So we consider the case when it's not 0. Okay, so we started with 0. We say that when it's 0, error exponential decays. Now let's consider the general case, not 0. Not 0, I differentiate. Okay, because s of t is c times c, e prime. Okay, so I can differentiate it. Now I differentiate it, right? So I take the derivative, which is like flexing the calculus, okay, right? So c times e derivative plus second derivative. Now I know what is e, which is the difference of, which is an error, right? So I go back to the original system, plugging it back, and I get equation 6. So now so from 6, what I do is I multiply this by s again. Okay. So I multiply s again. For some reason which I will explain later. So here s times s prime is equal to this whole thing, which is in 6 times s. Now I want to guarantee that this term is negative. Okay? So this is a kind of might seem to be a mystery why I assume that this is negative. But for the moment, let's just keep in mind that this term is negative if I take u, which is a control function, which I said you can design later on, if I take u to be this one. Okay? So basically, I take all positive terms with negative. So the negative terms will kill all positive terms, and then you're left with negative terms only. Okay? So I just kill all the negative terms. So this is how I design my u function. Okay? So that's my control function. So now I show you that it really does work. Next slide. So here I designed so-called Lyapunov function. So the Lyapunov function is a positive definite function. Here it's 1/2 times s squared. Okay, so positive definite means it is 0 at 0. Elsewhere it is positive. Elsewhere it's positive, right? Because it's quadratic function. So it's 0 at only 0. Elsewhere it's positive. And its derivative is negative definite, means that it's less than or equal to 0. That I guaranteed, right, from the previous slide. If you remember the previous slide, why? Why? Because here, what is the derivative of s? Now here, s is a function, sliding mode function, if you remember, of a function. Now, how do you differentiate a function, a composite function, from calculus? Which rule do you apply? Let me see if you remember. Students, please. Stage is yours. Now, if you expect, well, this is how I do my lecture, okay? So I force my students to talk as well, participate. That's why, I don't know, some of them like me, some of them don't like me, right? But it's a good way of, well, you know, keeping you interested to the subject, right? So, like, how do you differentiate a complex function? As first year calculus knowledge, calculus knowledge, analysis knowledge, how do you differentiate? Don't be shy. Why so? Promise I will not bite you if you give a wrong answer. Promise. It's not shame to make a so please. How do you differentiate a complex function? That is like f of g function. You want to differentiate. How do you differentiate? Anyone? Okay, so I encourage you to take math courses, but you have to remember what you learned. Okay? So you apply what kind of rule? There is this particular rule that you apply. What do you apply? What kind of rule do you apply? Now I give the answer, but don't forget, we apply chain. Chain, remember chain? Chain, right? So here you apply chain. So you apply the chain rule to differentiate this function s. So like then 1/2 will be cancelled. So by the chain rule, this is s prime times s. So this is why I get this s times s prime on the previous slide. So because I designed my u so that the sum of the terms will be cancelled out, right? So I get that all of the terms that I don't like, you don't like, would be just vanished. Okay. So everything would be less or equal than this function, this simple function. Okay, so that's the aim. Okay, so here, this is a negative term times some positive term, k times s squared. So that's my aim. Okay, so that was my aim to show that b prime is less or equal to some negative function, negative term times the b function itself. Now this is how I ensure that I got the Lyapunov function. Now Lyapunov, I can solve, I don't know, a lot about Lyapunov because they are together with the Poincare. We like regard them as the father of so-called dynamic systems. Okay? So Lyapunov is a Russian mathematician, engineer and mathematician. Poincare is a French mathematician. So they kind of lived during the same period, end of 18th century, beginning of the 19th century. And different from other like mathematicians, they were mainly focused on we call it now geometrical approach. Okay? So like qualitative approach rather than solving, finding the exact solutions to differential equations, which in nonlinear cases we don't have. So in differential equation course, like the introductory one, we only okay. So I'll give you a brief information. We mainly teach you how to solve linear ones. Okay. So then you don't stop taking introduction to differential equation course only. Okay. So you continue with nonlinear differential equations. Okay? So where we teach not to find exact solutions, but to analyze using some geometrical knowledge, like this Lyapunov function. Okay. So this one we don't teach in differential equation course, but we teach in upper level nonlinear differential equation. So what does this mean? Okay, so because you remember, I have now a linear. So because this one is a constant, linear differential inequality. Now, if you solve the right hand side would be again exponential decaying function. Okay, so this function will exponentially decay to zero. So that's the aim. Okay, so this is how mathematically we show that we design a function upon which your solutions will tend to zero exponentially. Okay, so this next thing. Well, this is the lemma, which I'm going to skip. Like the proof, I'm going to skip. Okay, so using this lemma, we show that. Okay, so the differential inequality will lead to this inequality. Okay, so differential inequality will lead to algebraic inequality. Here you see that now right hand side is this one is a constant initial v of t0, and here you have exponential decay function. Okay, so this means that the right hand side will tend to zero very quickly. Exponentially. All right, great. Good. Next slide. So back to neural network model. So that was like keeping up, warm up as a field. So we consider a simple differential equation from which I know now you have a sense how to design a controller, right? Now I do two more complex, like the model we have, champion inhibitor model, right? Which is nonlinear, discontinuous, and with delays, right? So it's like more complex than the example I considered in previous slides. So what we do here, again, I want to consider a surface S, so that your motion comes to that surface, okay, like converges to that surface with some control function, of course, that I will design like in the previous slides, and then it will forever be on this surface, and that surface is given by when you reach that surface, your constant is zero, so it's like the header is zero. Okay? So here, if what presented in model, I say that here is the model. Okay? You might ask, well, this looks like an imaginary. How do you find it, right? How do you find this control? But since I showed you the previous slides, on the previous slides I showed you that you start with an analysis. Okay, we did the same. You do the analysis. After some point, you want to kill some things. Okay, which very important. So you here we go like with this surface sliding motions. Okay. So this is something. This line is something to do with the model stuff, like with the warm-up time. So here, beta ij's are positive definite functions. With some constant k1, k2, they satisfy like k1 is like between 0 and 1, k2 is positive, and sine is the signal function, which basically tell you that if you have a positive function, then it's plus 1, right? Negative function is minus 1. It basically tells you the sign of the function, nothing else. Okay, so signal is the sine function. So then what we do is, so this is our surface. We want to show that it does work with that control. So we differentiate this surface, and then you get this function. Okay, so like the rest is like how you differentiate from here to here is the columns. So you differentiate this with regard to time, right? Things like this. So then, as before, you want to see that you want to find T0 so that ST is equal to 0. So as before, we started with this S function equals 0. And if you remember, I obtained the solution, which is exponential decay. And in general case, I said, okay, not 0. You differentiate, then you do some magic, like analysis, you find what this E function is. We do the same here, but with like more complex model, right? So this S is equal to S prime is equal to 0. You solve this, and then you end up with this equation, differential equation 11. So this here you want to see that the state variable, which is your voltage, will converge to the sliding surface in a finite time. So you do so-called reachability analysis. Okay, so you want to understand at what time does your system merge to this surface, sliding motion. Okay, so that's the reachability. So if you reach, then we do analysis, then you see that by the definition, it should be 0, right? Now, what happens if you don't reach, right? So, like, something like, I sent my, plane, right, or some shuttle to say that to move, right? So, first, it has to reach the moon to do some expedition or something. What if it doesn't reach? So, it doesn't work. You don't collect the data. So, here, it's the same. You do a reachability analysis. Not only designing the surface is important, but the reachability analysis is important here. So here we prove that this is really, you reach the surface in a finite and infinite space-time. This next one. So here we have control over Wij function, which is our control function. Okay, so here I have my phi, which I will take as this term, as here I define phi function here, and I have a control over this W function. Okay, so next. Okay, so in this theorem, we prove that this sliding mode surface does really work with the control function design. That is this Wij, okay, which is given by 12. Looks scary, yeah, I agree. But the model itself is not a simple model. So if you remember what's a complex model, it comes from complex neural network. But I give you a sense with a simple simple example how you can design a controller, right? So here we follow similar approach, somewhat similar approach, and we do prove that it does reach the settling time in your surface at this T star, which is somewhat depends on your initial condition, CIJ0. Okay, so we really have that. This part right hand side is a constant. So this is the sum of CIJs, zeros, at the power of 1 minus K2, but K2 was somewhat positive. Right? And divided by this one, but K, okay, so where beta is or beta functions over IG. Alright, so the next one, next slide, is we show the proof. No, I'm quite sure that you are not interested, but we have the proof here. The ones who are interested, I would just say that it is somewhat similar to in the example we used. Okay, so the aim is to show that this is, we choose the diagonal function here, b to the sum of its absolute value of SIJ functions, and then take the derivative, and at the end we show that the derivative is negative definite. And it's not only negative definite, it's the power of the function. Then we apply some lemmas that I skipped in the beginning, okay, then we show that it really does approach the surface information. Okay, so this is the okay, so then what we do, okay, so we prove that this T star really works as in definition 1 that I gave you before. What is it? Fixed time, I'm sorry, finite time synchronization. The limit of the error should tend to 0, right? T star, and then it remains 0. So we do prove that it does satisfy this definition. So this one is so we check that the same surface, using the same surface, we can, and same you can reach fixed time synchronization. But here, look at the Tmax, okay? Now it does not, it is really a constant which doesn't depend on the initial condition. If you remember the previous one, it depends on CIJ zeros, which is initial condition. Listen, every time you have to check the initial condition. Here you don't have to. So that is the difference. Okay, so on the next slide, we prove that it does really reach synchronization at Tmax. Next slide. But so we do consider only 2 conditions. We show that this Riemann response system, they do achieve fixed time synchronization, the same controller, and then Tmax is given by this. This next slide. So here is the proof again. So we design here a different Lyapunov function. Okay, so analysis is made by different Lyapunov function. Here the sum was, if you remember, the sum in the previous proof was the absolute value of all SIJs. Here we take squares, sum of the squares. Okay, so it doesn't work, and then you should show that it doesn't work at fixed time. This next slide. So here again we show that now it satisfies definition 2, where we say that it does not only reach synchronization at fixed time, but this fixed time doesn't depend on initial conditions. So it's a finite time. I'm sorry, not only finite time, but it's fixed time. Doesn't depend on initial conditions, CIJs, so it's fixed time. Next slide, please. So here, I don't know if you can see, here are the simulations. So simulations of the model without controller. Now you can see they are of different color. Okay, so you can see that here we consider 2 by 3, or like simplicity. Okay, just even this simple model, you simulate it on computer. So you see that the solutions do not synchronize. That means they don't go to, they're not like. If you consider the error between the functions, you can see that the error is not zero, right? So, like, we consider an example where we do not synchronize. Okay, please, next slide. And then you apply control function that we found in theory, the sublayer. And you can see that this blue and red solutions they synchronize very fast, like less than, in all cases, it's less than 1 second. Okay, so in less than 1 second, you can see that both solutions are synchronized. This means that they become sync. So the error, like within even less than, like around 0.5, right? 0.5. Even in this case, even less than 0. Less than 0. Less than 0.5 or equal to 0.5 seconds, your nodes synchronize. This next one. So how much time? How much? I didn't ask about. Okay. So I think I'm finishing. So that was about sliding mode control. And that might seem like, well, unit to which I would agree. The differential equation, only the differential equation. So, but with the mathematics, you can see that upper level mathematics, you can prove very sophisticated stuff. So the conditions we got, I'll say, in mathematics, say that they are sufficient conditions, sufficient to reach synchronization, but they are not necessary conditions. Which means there are many open problems still. There are many open problems. Like you might say that, okay, I consider a different controller and using different Laplace function, I prove that I improve your result. That's possible. And I say that's quite possible. So like there is a lot of room to study in this field. And now, as I promised, I said, even using some calculus knowledge, you can prove some good results. Okay, but here we assume that the model, which is less realistic, of course, we assume that there is no delay. So the delay term is we ignore the delays. Okay, so it's become a nonlinear differential equation. So here, if you look at the activation function, okay, so we assume, so to make good things, we drop back. We don't assume linguistic, means that my TIJs are now continuous. And you can see that no delays. But, so delays could be kind of compromised by if you assume here, okay, so we assume and or operators. So this is like in computer science, you know, right? What is and operator? That's all operators. So here we do it by this, right? Because so this comes from we call it fuzziness. Okay, so like, am I tall? Like the question is, am I tall? Might be a relative question, right? So is the weather like is it good? Right? So, but it might depend from person to person. The person who comes from, I don't know, might say that the weather is not good, especially in our country. So it is -10 in January. We said the weather is perfect today. Let's go outside. Which might not be the case for you guys. So the weather, the coldness, everything is related. So that, you know, like in computer science, we model in mathematics, we do model using the fuzzy theory. It's and, or, and so, right? So we have this and or operators, but we and the delays are introduced here in stuff like the activation function. But all of these functions are considered to be continuous, not discontinuous like it was before. Okay, so next slide, please. So we modify the model, and the aim remains the same to design a. Okay, you look at the error function. You want to design a control function so that this error tends to zero. So then, for simplicity, we define these RAJ functions, all this nonlinear stuff, RAJ, and I leave the linear stuff, plus these PIJ control functions. So then the model looks simpler, like in 14. Next slide, please. So here, in addition to two assumptions that we made on the activation functions, that is, malicious continuous and bounded, I assume one more condition, this one, which looks very scary, okay? Which, anyway, but you might even ask, can I find a function which satisfies this? And the answer is yes. It's not easy to find. The answer is yes, but we'll show it later on. So the aim is to find a T so that for your response and drive system, the error between the response and drive system tend to zero in a finite time. Next slide, please. Okay, so here the first lemma says if your initial condition is bounded, which in reality is bounded, initial condition, because you start with that bounded initial condition, right? So then you can show that your solution would be bounded. But the conditions I assume one more condition to the existing condition, right? So this is continuous boundedness. I assume one more condition. So then that would be enough to say that this controller, PIJ, would work like there is a discontinuous one, okay? Would work to control the network. Then we say that it reaches finite time synchronization and would precisely give that T star I called in the previous slides, but here I call it T0 to distinguish from other slides. Okay, please go to the next slide. Now what we put here is we apply so-called maximum principle in calculus. If you remember, like we say that we show you that applying first and second derivative, you can show that the function either it contains local minimum, local maximum, right? Global maximum. Okay, so suppose that you have local minimum or local maximum. So you can show that that's called local extreme, right? In calculus. So we show you, suppose that you have a parabolic function like x squared, right? So x squared function, does it contain a minimum? Let me ask you a question. Yes, x squared, a simple function, x squared. Assume x squared, a parabolic function from high school. Does it attain a minimum? Not all functions, but this particular function does have minimum. Right? So like, assume that what is the shape of x squared? That's a parabola, right? Down the block, so upwards looking parabola. So this attain a local minimum that you can show using a second derivative test. Like, first derivative test. You look at x prime, like, take the derivative, x squared, x 2x is equal to 0, then you find x is equal to 0 using local extreme. In fact, it's a global extreme, global minimum. So because x squared is always a non-negative function, and 0 at 0, like the Japan function I consider, and that is why you can prove that sometimes global extreme is local extreme is a global extreme, right? So here we do apply the same. To show that, a drive system, response system, and the aim is to construct a function so that it attains 0, then never leaves. You remember? So I consider the difference of these functions, and the drive will be this one. Next slide, please. And then I have this lemma, which I leave as an exercise. If you take calculus, I'm quite sure you should be able to do this. To show that this function is always non-negative if a is larger than 1 over e, for positive x, of course. So this function is always non-negative. So this is, I see here it is straightforward enough. Now, anyone who took calculus course, in my view, if you like, let me see who closed line, who got A from calculus, A from calculus. No, I won't ask question, don't be shy. A from calculus. Math course, A from math course. You take math course, right? Is it no math course yet? Okay, marks. Okay. So if you got the high grade in math, let me see those. No one. Really no one? Right. No, I'm sure you there are. Okay, so I expect you should be able to predict. And the hint is, it's like if you consider two functions. Okay, so it's like I said, first derivative is equal. Yeah, it's very well. So next slide. And using that calculus, which I showed you, we show that it's Pij and Qij, so which then look similar to the previous function we have, x times ln x, okay? The sum x plus ln x, ax plus ln x. We've designed a controller in that form. Design a controller so that you reach the synchronization, finite time synchronization T1. Okay, so here it is possible to prove that you really reach the finite time synchronization, but fixed time would be difficult. So then I should say what is the Lyapunov function here. So it is k, like the absolute value of eij's plus rij's. And makes like this. So not only we do prove this to inertial terms, but we do also prove it a model which includes diffusion. Okay, so from application point of view, if you are working on a 2 or 3 dimensional, then you have to consider not only time but also state. And then there is a good motivation to study with a diffusion term. Okay? So and then like we have that becomes then not ordinary differential equation, but mathematics we call it partial differential equations. Okay, so the model itself becomes partial differential equation, which becomes more sophisticated, but fortunately, we do have maximum principle again for PDEs. We call it PDEs for short. Next slide, please. So here, so the error function is defined similarly. So with the help of this memo, which I'm going to skip, the proof will be skipped. Okay, so if you're interested, I can share. We prove that we reach finite and fixed. Finite time synchronization. On the next slide, please. So on the next slide, this is the same lemma as before. Next slide, please. This too. So we prove that we do reach a synchronization here. T is given by this huge number, but since this does depend on eij 0x, which is the initial condition, we say that it is a finite time synchronization, but not fixed time. Unfortunately, here we haven't achieved any fixed time synchronization using these control mechanisms. Okay, so as I said, it remains as an open question. So please, next slide. So here I show you the simulations. Okay? The simulations show us that really these ones are synchronized. So the blue ones are drive system and the red ones are response system. So Then these ones are for ODE model. Next slide, please. And these ones, the upper ones are, if you look at the error functions, they tend to 0 in 5 seconds. What is it? 5? This one is in 8 seconds. And this one would show you that, because I said we consider not only ODE model but the PD model, you can see that the error function here, in three-dimensional case, we show that it tends to 0. So then it remains 0 for them. So these are the illustrated examples we have. Next slide, please. And of course, I have to say a few words about my collaborators. These works wouldn't be possible without my collaborators from here, Coimbatore. It's Professor Akepan from Bharathiar University. Okay, and my postdoctoral scholar, Sound Rajan, who's also from Tamil Nadu, from a different university. Okay. And two of my graduate students, Madina Okil and Jangir. So Madina and Jangir did main we give them directions, but the main job was done by our graduate students. So I hope in the future we'll be able to conduct a research something like this. And I'm also thankful to a fund I received from Science Committee of Education, Ministry of Education, and our university. So that's it. I'd like to next slide. Thank you for your attention. And if you have questions or short questions, I'll be happy. Long questions, emails, please. Thank you.
Any questions from the participants, sir?
That's a good question. That's a good question. No, as I said, the question is there any system that can be synchronized? Well, the problem of synchronization really does depend on the control mechanisms you design. So if you are able to show that it does the synchronization is not a word, as you can see here. Okay? So initially, you like the networks reconfigure even not synchronized. But the question of whether or not it's possible to find a controller to any system is, I think, considered to be NP-hard system. NP-hard problem. Okay, it's almost impossible to answer immediately. Yes, so like in mathematics we say that hard problem, NP-hard problem, and that we consider their question in particular we consider to be NP-hard problem, which is ABC. Right. So, not control. That's fair. What that I would say might be so you really so for this system quite sure. As I said, I'm currently working on an application where you can apply this surprisingly to me, or maybe not surprisingly to you, to image encryption and encryption. It really does work well. Okay, so you give me image, I encrypt it, and if I tell you the control function, you can do something. You don't have to know encryption. Okay? So that works well with initial results that could be able to encrypt the image and decrypt. Okay, so in that case, no pain. But yes. Okay, so we are in the progress of drafting the paper. So that would be published later on. That might be interesting to this audience, I hope. Not this mathematics stuff that I presented. I feel that. Maybe next week. Next time. Okay. Additional question. That's a very good question. Yes. Yes. Well, again, no direct question. Okay, so no immediate answer from question. Okay, so you give me model, we get together. Then, like, as the principal said, there might be collaboration. Okay. All right, good questions. Thank you. Any other questions?
Questions from the audience?
Differentiate f of g function.
Which one? So I answer this. So so this is a you apply a general. Okay, so you're asking a complex function. So this is like okay, so unfortunately I don't have this a board. There's a whiteboard. So what is f of g derivative? So it is f derivative g of x multiplied by g derivative. Okay, so that g derivative is also important. That's the answer to my question. And that I apply to s squared. You can't plainly take the derivative because it's a function of function. Okay, so it's an error function. S is not just a variable. It's a function of function. It's functional. So in differentiating this kind of function, you have to be careful. That's what I want to emphasize.
And even in fixed terms, in the theorem, in fixed terms, both theorem we have an assumption like A1 might equals 0. And what is that A1 and A2?
Not zero. So this A1, A2, these are the assumptions. Okay, so if you go, so like
Both the theorems we have the starting assumption as
yeah. So go back. Back. Oh, yeah. Go back.
I think
Yeah. It's like these are the A1 and A2 assumptions. So this I explained that A1 is something like that activation function is a mixture continuous and it's only. So we need them, as I said, like to have unique solution and bounded solution. Unique bounded solution. So it's not minus what both A1 and A2 we need two conditions. So it's like we want to stop models which are bounded. That's what it is. Okay, I think that's it. I would like to thank you again for inviting me, organizers of the committee. I'm very happy, delighted to be here, and I hope sometime in the future.
thank you, sir. Thank you so much for your effective presentation. We have learned a lot more about, you have started with the synchronization and you have dived into the applications of neural networks, a few more applications what you have given. And the explanation of the formula was pretty good and it is easy to understand. Even though for us students it's not a cup of tea to learn our differential equations, but definitely to take it from your words and we'll ask our students to undergo the course in differential equations in the future as well. And definitely that will be useful for their research and their projects also. So thank you so much for your presentation. It's quite interesting also. Thank you for the audience as well.
Students, it is followed by the paper presentation. இங்க உங்க ஸ்டூடெண்ட்ஸ் தான் பண்றாங்க பேப்பர் பிரசன்டேஷன். ஒரு சீஃப் கெஸ்ட் இருக்கிறாங்க, அவங்க போறதுக்கு முன்னாடியே நடந்து போறீங்க, பேசுறீங்க.
Now, what is the don't Oh,
சார் என்ன இது இப்போ இருக்குதுங்களா? சரி சார் டீட்டெயில்ஸ் இருக்கா? இப்போ எங்கே இதுலேயே இல்லையா? இஎஸ் செமினார் தான் பண்ணுறீங்க. அதே மாதிரி தான் வீடியோ பார்க்குறீங்களா? பில் பண்ணி தான் சார் இருக்கு. இப்போ ஒன்றும் தெரியலையே. இப்போ இது வரைக்கும் நான் ஷேரிங் போட்டிருந்தேன். அந்த இமேஜை இப்போ தான் எடுத்துட்ருக்கேன். காட்ட சொல்லுங்கள் சார். தீரஜ் இன்னும் வீடியோ இதில் வரலையே சார். சரி. சரி சார். ஓகே சார். ஏன்னா திடீர்னு எனக்கு சுவிட்ச் ஆஃப் ஆகி போச்சு. ஆ ஆ
numerical solutions. It's fit very well. That means it's always the case when you do the science and computation. And I heard that many of you are working on the computation field. And computation fields are more like mathematics. So you have some all computer improve your and people that's and I'm just doing it. And I also do design and on ask them to do the experiment. And when you do the experiment, that's a better technology. So you can have comparison between the numerical and the experiment. So when you calculations right, it's always explain what you're doing and what you did in numerical is correct. Because the numerical is mathematics, you're solving mathematics, and this is only approximation. I shouldn't have said only, but it's approximation. Yes. When you solve the nonlinear system, like a Navier approximation, it's a nonlinear system. And those people who are working on the mathematics and differential equation, usually differential equation is a nonlinear. What nonlinear means? Multiple solutions. Always there are multiple solutions. Okay? But in natural science, solution is only one. Do you remember that? Only one. Only one means what you're observing in front of you is an answer. It's a correct answer. But what you're working in mathematics, solving mathematics, has many answers. Yeah? So you don't know which one is correct. Yes. If you're doing only mathematics, many of it, okay, whether it's converges or diverges, that is a problem. But only one we did an experiment. So when you can have the velocity during generating in a sphere. Okay, so you can look at it. So when you look at it, you can observe. Next one, please. That was 1964, when, as I said, the real substance of magnetic ray was invented, not in concept. What I said in the 17th century, Sir Harry was only concept. Magnetic rays are there. That makes aurora. That causes phenomenon in northern light. But actual substance made in 1964 in NASA. And the man is called Lessland Rosenzweig. Lessland was a director of NASA at the time. And he wrote a paper on what can magnetic ray be made. And what's the vision for that? This is only conceptual. I was not very very eager to work and what I'm going with. I was very keen. And I come across that TSI, this is dynamics, perhaps theoretics is and the TS diagram is a gas. Yeah. It's gas. Yes. And the gas diagram it can be written is the standard PV. And that you roll P picture and N is 14. This is a thermodynamics basic concept. Second law and the first law of thermodynamics. But I was very surprised. That man, Lessland Rosenzweig, brought TS diagram in terms H and M. H and M is a magnetic parameter. And magnetic parameter. It comes from physics. I never knew that TS diagram can be drawn by M and H. And I was very moved. And I looked at it. I don't know how many times I read this paper. And then I just come across, all right, I made that concept in a real equipment. My basis is mechanical engineering. So if I ask my student, postgraduate student, they can make it. Next slide, please. And at the same time, the people working on the boiling phenomena. As my PhD, I come from the University of Manchester, and I was doing thermodynamics. Also, I was doing heat transfer, boiling heat transfer. Then I just used my knowledge. I put some boiling phenomena into the magnetic relief. This is what I wrote some papers. Next one. And based on the knowledge, and I made a little equipment. I have some patent on that. I put some magnetic fluid in a cell. And the cell contains magnetic in some section. One part of the cooling, and when you apply the magnetic fields, that's you can just put some permanent magnet on that, and then the disk rotates by itself, only by heat difference, temperature difference, no mechanical, nothing. Just when you have temperature difference, the disk rotates by itself. Yeah, and then it's rotate. And really, you can rotate. You can see that. And I calculated that some efficiency is very low. 10 to the power minus 3 efficiency. Almost nothing. But the important thing is to rotate. You can make it a more bigger scale. You can even generate electricity without free cost. Just heat difference. Say, for example, the temperature in this room is a little bit higher than outside. Okay? So if you have a large disk, one part of this is here, one part of it is outside, and you have a very big magnet, the disk rotates by itself. And you can generate electricity. This is what is said. Okay? While working on this equipment, I just come across the heat problems. Next slide, please. And this is what we call it natural convection. And this is also very important in the heat transfer in some physics. Yes, there are some kind of mode how the heat can be transmitted. We have 4 modes of heat transmissions. One is radiation. Radiation comes from sun. Very long distance. It's nothing, only by walking space. And we can have a heat. And then there's a clock which is like transmitted from one side to another. If we have temperature difference, it's convection. And convection is like a liquid rotating or liquid circulation. Carry the energy. Natural convection and forced convection. 2 modes of convection. So, a couple of things. But I was very interested how this inside of this can be made. You can't see that inside of the cell. But I can imagine. I can solve the equations. I solve the equations. This is a result. Natural convections. You can see when you solve the differential equation, you can get all the answers and a nice picture of how the temperature distribution. This kind of thing. Okay, next one, please. Next. Yes, then I made actual using on the basis of body. So I made another equipment. It's called a heat pipe. And this is also science can be used in practical way always. When you know that actually what's the rule or what is the sort of function of the devices, you can all storage, transfer, and I make equipment that can transmit this part. So this is very much those people have those people are working on this calculations and do a lot of calculation from that. The heat pipe is the equipment that can transmit the heat like a conduction. It's interesting, you know that. You know the piece of bark, metals? When you have one end warming, one end cooling, the heat is transmitting from warm to the cool part, depending on the temperature gradient. Heat flows by temperature gradient, not by itself. Gradient. When you have gradient of heat temperature, you can transmit it. Okay? This is called the conduction. That when you have a gas inside in the heat, and then warm it up other end, and cool it another end, you can also transmit the heat, not by conduction. It's called forced convection. And also when you have latent heat, evaporation means you can have a more heat. Because heat transfer more is convection is higher more. When you have latent heat, boiling, phase change, you can have more heat transfer. That means when you make equipment quite light, you can transmit large amount of heat. Okay, this is the equipment I made using a magnetic coil. Next one, please. Okay, the actual equipment, I ask, I'm belong to my student, like you, a postgraduate student, a PhD student, I always ask them to make equipment by themselves, not to buy it. Okay, so that when I ask my student, I always ask them to put your idea on a piece of paper, any idea. A piece of paper and draw, sketch it. Then just think about it, looking at the paper, do your own sketch, then put actual drawing, we call it mechanical drawing. Once you set up mechanical drawing, when you ask to the technician will make it. Okay, so the important part is mechanical drawing. Okay, so the student, sometimes they make themselves, but bigger part, they can ask the technicians to make. So I ask the student to make equipment. Next one. And then this is a data. And I compare it with conventional heat pipe with our equipment. And our equipment can transmit heat like 10 meter and say this is 1 meter and 10 meter. Okay? This is about the space technology. The heat pipe is using artificial substrate going around, okay, carrying the heat upstairs. Yeah? Then our equipment carry even 10 meters length of the heat compared with the ordinary heat pipe. Next slide, please. This is what I explained before. We have 4 distinguished modes of heat transfer: conduction, radiation, and our heat pipe. Our heat pipe can carry, look at that heat flux, 64 watt heat can be carried with this equipment, right? Okay, next one. And this is also very basic research in fluid mechanics, where like measuring the bubbles, like how much bubble is contained inside the pipe. It's a big problem with some oil company in Kuwait. I'd like to know how much gas is coming from when you have oil coming from deep sea. And gas and liquid on the water space where you come to this. And they know how much gas space contained in the oil rig. And I just suggested that some tiny amount of magnetic materials inside, like a powder, iron. If you can mix with iron powders, even you have very small amount of radiation inside, your hot can be contained in a gas pipe. No, it hasn't been materialized, but I put some idea on that. Did a bottle experiment and I carried the numerical. But some difficulties that it's very difficult to put it in oil well. Yeah, but it should work. Next one. And this is one of the experiments we did it, and we have set a theory on it. I had a PhD student with me, and I asked him to carry on. This is very difficult. So you have to read the data, yeah, from the equipment. And this is he did it a wavelength transformation. This is mathematics, wavelength analysis. And he did some analysis in France. I sent to the France because they are very good at mathematics. And he obtained a PhD from Paris, and also one PhD from myself. So he has simultaneously two PhDs doing this project. Okay, next one, please. You can see that you can estimate how much bubbles contained in the flow. It's like ink, right? Very black substance. You can see how much is going on just by picking up the signal. You have to read the signal anyway. Right? That's one. And also bubble experiment. This is you can see the bubbles. Next one. Also, simulations. You can solve simulation equation, and you can get some bubble generation, shape of bubbles. Right? You can predict. Next one. That is a natural convection. It's very important. It's come from original work. And this one is a natural convection in a space. In space, when you go upstairs, you have no G, no gravity there in space. We have G here, 1G on the surface. Then when you have natural convection can be only generated by under a G. If you don't have a G, you won't have a convection, only the convection. So that problem is that when you go upstairs, go up to the space, there's no G. So the heat transfer mode is only by convection. Convection mode is very low. You cannot carry a lot of heat. Introducing magnetic fluid type, G can be compatible with called the Kelvin constant heat. And the H is almost simultaneously you can generate the space. That means you can convection in the space. This is what is numerical. Yeah? And also this is as well. From this, I found this very interesting phenomenon. It's called the chaos. Chaos is mathematical problem. When you draw the Lorentz attractors, okay? That is the phase space. And you can see where the phenomenon is, the chaos on shows so that when you have a natural convection inside, when you look at the natural convection with particle, you can just find out that chaos phenomenon, nonlinear physics, and nonlinear phenomena can be observed. This is too difficult for students to do this. Too much mathematics only. So just skip over. More. You just come about going forward. This is also my current research. Let's see if it's before the problem. Yeah, this is interesting. Okay. Using my viscoelastic research with magnetic fluid, this is a very current my achievement. You have a magnet, okay? Magnet materials. you may not run the Maxwell equation. Maxwell equation is an electromagnetic equation. Fluid dynamics is a radius-Stokes equation. So when you look in the Maxwell equation, you have a relation between n, s, and n. N is a North Pole. S is a magnet. You can always say S and M. So how do you put S and M in a magnet? It's my problem. Okay? So with magnetic fluid, we make a liquid-like magnet. And using a magnet under magnetic fields, you can have a permanent magnet, a solid magnet in your hand. So I asked my student again, can you make a panda? Nice funny magnet with a black and white. But the question, how is magnet? Okay, white part is S, black part is N. Can you think of it? Can you make a little panda with a black part is N, white part is N. It is like separate N and S. That is what the Maxwell equations. Okay, the Maxwell equations say cannot separate N and S. You can't only have S in hand. You cannot N in hand. Well, science in space. And some we analyze, but nobody knows whether this is true or not. We believe the Maxwell equation is true now, yes. But I asked the student using making how great. But you can make it like it, very similar to that, so that the arrangement, how do you put N and S in the material is a problem. Yeah, this is casting problem. So when you have a liquid like magnet, when you casting like making plastic, the liquid thing you can make a solid. Under magnetic field, you can do the magic. Right? Next slide, please. Here. This is almost my final talk. And also I'm giving some questions. Monopole, does it exist? No. Answer is no. But you can make very close. Like this. I can make like that a magnet. Inside, red part is N. Okay, N. That blue part is S. So you can almost separate it. But this kind of thing you cannot make. You cannot make it with a sticking magnet together. You can always make it under magnetic field. And you can mold it. You can make it in one piece. You can make up like that. But you can still have N and S separately. Okay? So the question is, can you make a sphere? Spherical surface is S, inside N. The point is no. No. You can't make it like that. This is the monopole. Whatever you do, you cannot make S and N separate. Yes? But instead, you can make like that sphere. It looks like a peanuts. Spheroid, but this is a sphere. Okay? Depends on this screen. Like this. You can have a distribution of the S, N in the equator. Another part, S is some other person. Okay, all together. Finish. Sure. Okay, finish. I tend to speak too much. Someone has to stop. Okay, this is a good time. This is the end of my talk. And so far, I can separate and make like a sphere with distribution and okay, this is my end of my talk. And thanks for listening. Okay, thank you. and your patience.
Thank you for sharing a wonderful Now I call upon Dr. Sridhar Ritesh to announce the achievements.
Yeah, good evening to all. So I am really happy to announce the Best Paper Awards for this international conference. We have the first person, Omnia Sayoni from Khalid University of Abu Dhabi to receive the Best Paper Award, and T. Kosai Roman and Dr. A. Nirmala from Dr. NGP Institution, and S.S. Sudha from Dr. S.S. Rajagopal College, S.S. Beulah Bennett from Jan University, and we have two more persons from our own institution, Bhavya and Shri Krishna, and we so won the Best Paper Award.
Thank you, sir. We request the dignitaries to release the conference proceedings. Thank you, dignitaries. Thank you, the best prayer that anyone could say. It expresses extreme gratitude, humility, understanding. Now, I would like to call upon
All students please together.
have a photo session. Thank you is the best prayer that anyone could say. It expresses extreme gratitude, humility, and understanding. Now, I would like to call upon Dr. Sridhar Vignesh, Professor and Head, Department of Information Technology, to deliver the oath of office.
So good evening to one another once again. It was indeed a great pleasure again for me to render word of thanks on behalf of institution management, the special principal, the special heads of various departments and faculty department friends from all the computer training departments and all the student friends. We had a wonderful resource persons from 3 different countries, Kazakhstan, sir, and Ankit sir, and Mr. Yoshia from Japan, and we have Samuel from Singapore, and we do have 2 different resource persons from our own India who have been delivering a wonderful keynote sessions on various emerging topics that is prevailing in the industry, and they have given us a glimpse how these technologies are actually ruling the world in current trend. Okay, I hope that the learnings that student fraternity has received from these keynote sessions was marvelous, and they will be implementing those things in their future career. So, with these words, I once again return my sincere thanks to all the keynote speakers, and I'll be failing my duty by not thanking the participants from various institutions who have presented their research papers, both in innovative research as well as in interpretive research, and they have been sharing their knowledges. I also congratulate the students, the young graduates who have been doing their study work on the first part of their research and presenting their papers in this international conference, and they all proved that they have did their work to a marvelous extent, and the reviewers have given very good feedback on seeing the papers that is being submitted by each and every contribution that is being made by the graduates, right? So with these words, I once again thank each and every member for their valuable contribution in this international conference on computing and intelligence system. I will very my duty if I am not thanking the conveners, organizing secretaries, the organizing committee faculty members, and all the teaching and non-teaching faculty members who have been working for the past 3 to 4 days and in making this international conference a grand success. So I thank each and every member once again. I also thank the MCDS members who have been doing a wonderful job in all the sessions. Whatever that is being done, they have also did it in a very short period of time span. I thank the MC members too. Thank you. Thank you. Thank you all.
Thank you, sir. Now, I request everyone to rise up for the national. We have come to the end of the session. Thank you, audience. Please stay back for a minute. Please stay.
Okay, sir.